Our third and final speaker of the session today will be Mahsa Varshosaz, talking about formal specification and testing for reinforcement learning.
Hi, yes, thank you. Hi, my name is Mahsa, and today I will be talking about our work on formal specification and testing for reinforcement learning. So let me start with an example of reinforcement learning. In general, reinforcement learning is concerned with learning control policies for an agent in order to achieve a goal while interacting with an environment. Here you see an example of an agent that is a moving car that moves towards an obstacle. And the goal is to learn an optimal policy such that the car would brake before the obstacle and it would also avoid sharp brakes. So in other words, what we are interested in this reinforcement learning setup is to learn a policy that would tell us, given a speed and position of the car, what is the required deceleration to apply in order to achieve the above goals. So in general, the learning usually involves running a set of experiments, and the car selects some deceleration value in a specific state of the environment, and then it observes a reward, and by accumulating these rewards throughout different experiments, at the end we know what is the expected reward for taking an action in a specific state of the environment, and based on these values we can obtain a policy that will tell us what is the best action that we can take in each state of the environment, or in each stage of the agent. So usually reinforcement learning research focuses on evaluating the quality of the obtained policies through this process. But the policies something can go wrong when we learn the policy, and the policy might be wrong. And the cause of getting a wrong policy can be either because of a bad design, or it can also be because of bugs happening in the implementation of different components that are involved in the process of reinforcement learning. But finding these bugs in the components or the implementation of the components involved in reinforcement learning requires systematic testing. But at the moment, there's a lack of testing or techniques and tools that can be applied for systematic testing of reinforcement learning setups. And in general, also, there's a lack of correctness specifications for the reinforcement learning setup. So in this work that I'm presenting today, we develop a partial correctness specification for reinforcement learning, and also we develop a method to test temporal difference algorithms, which are a class of reinforcement learning algorithms. And also our long-term goal as a continuation of this work is to develop and test reinforcement learning applications more systematically. And a side outcome of our work is a well-tested, configurable implementation of the 3D reinforcement learning algorithms, and also a test harness that includes a quick check style test that I'm going to explain throughout this presentation. But just as a first step, we have formalized the reinforcement learning setup as a tuple like this. And this is a very common formalization for the reinforcement learning setup that one would find in reinforcement learning literature. So we define a finite infinite set of states that describe the state of the environment and agent, a set of initial states, action, and a set of observable states that are states that represent how an agent observes its surroundings. And then also there are a set of functions that, for example, we have an observation function that maps the state space of the environment and agent to the set of into the set of observable states. A transition function that is a probabilistic transition function that tells us, given a state and action, where we are going to end up in, which state we are going to end up in, with what probability. And then we also have a reward function that tells us, given a state and action, what is the reward that we are going to observe, and a function that will tell us whether we are in a final state of the environment. But the more interesting part is about, in the formalization of this setup, is about how we can describe or specify reinforcement learning algorithms. So let's first have a look at the existing descriptions of the RL algorithms in the reinforcement learning literature. So this is a standard impure representation of the well-known SARSA algorithm in reinforcement learning. And here I will not go into the details because of the time constraints, but rather just in a higher level tell you that in general there are, so SARSA involves starting in an state and taking an action and observing the reward and observing what is the next action. So we call this a sampling. And then also it samples the next state in the target state. And the important part is an update that happens in SARSA, which is updating the value of an action in the state that we have started from based on the new observation that we have seen. So based on the reward that we have observed and also based on the value of the next state and action. So we are updating the value of a specific action in a state that we have started from, and this is the core of the SARSA algorithm. But this is a typical representation that what we would find in the literature. But let me just highlight that what are the problems with this imperative description that we have here. So because of the presentation that you see here, there are many details and intricacies that remain hidden because of the type of presentation of the algorithm that we have that are crucial for obtaining a correct implementation of the algorithm starting from this description. So for example, the reward that we observe, the value of the reward would depend on the action that has been sampled and also the state that we have started from, or the epsilon gradient policy also depends on how the values of the Q are calculated. Also the sampling of the next state remains implicit in this description. So not knowing these details explicitly can cause errors once we start from this description and moving towards an implementation. Furthermore, there are also a lot of commonalities between different TD algorithms that remain hidden because of this description that cannot be appreciated while we are implementing these algorithms. For example, here you see two visual representations of steps of two TD algorithms. So these visual representations are called backup diagrams, and that represent the main steps that are taken in each of these algorithms. And as you can see, the commonalities are more visible in these backup diagrams rather than in the textual representation or description of the algorithm. So these commonalities cannot be also appreciated while we are implementing the algorithms based on the current descriptions. And additionally, the TD algorithms, as they grow, and there are TD algorithms that not only take one step ahead into account in their updated step, there are more complicated TD algorithms. So as the algorithms grow, the description becomes more and more complex, which can cause even more errors in the implementation, just considering the description that we saw. So our solution to address the current challenges that we see in the imperative descriptions of the TD algorithms in the literature is we propose or move towards a more declarative description of these algorithms. So we propose BDL, which is a domain-specific language that can describe the backup diagrams that you saw that visually represent the main steps in the TD algorithms. So we use this or propose this domain-specific language that can describe the main elements that are included or that are contained in different backup diagrams of the TD algorithms. So this is the syntax of BDL, the language that we are proposing. So BDL involves first estimation terms that can be of type sample or expectation, and then also A BDL term can include a chain of estimations, which are the upper part of the backup diagram, followed by the last step, which is an updated state, and followed with a sample or an expectation step. So here, for example, SARSA, the algorithm that we saw before, this is a backup diagram for SARSA, and the BDL description of SARSA is something like this, that the first term in this description corresponds to this part, or the first element, which is a sampling element in the backup diagram, and the second part corresponds to an updated step in the backup diagram. So in other words, BDL is capturing the semantics of the basic blocks of the backup diagrams, which are the heart of the temporal difference algorithms. So this is the BDL description for different backup diagrams that are representing different temporal difference algorithms. So this is the textual representation using BDL. And now we can describe the semantics of different terms in BDL. So we describe the semantics in a denotational style, and which gives us an interpreter for BDL terms. And what is generated using this BDL interpreter gives us the full semantics of a backup diagram that can in turn be considered as a specification for the temporal difference algorithms. So let's have a look at the semantics of BDL. So I will just explain the semantics of the sampling terms for BDL in detail. So here you can see that the semantics is of a sampling term in BDL is described like this, and the semantics is executed in a probability monad, and here you can see the monadic bind. And what is described here is that starting in a state, an action, and given the current accumulated reward that we have, and here this is the discount factor that is required in the updated step, so it's a value as well. We say that we can perform a transition, so sample the environment, and then we can observe the next state. And here that is the unit operation in the probability monad. And so it's a deterministic or the Dirac distribution. But the important point about these steps that you see, or these compositions that you see here in the semantics of the sample term, is that we clearly know where each of these elements, for example, the next state or the reward or the next action would come from, or how they are calculated. And this helps us to go from these semantics to an implementation, directly go to an implementation of the algorithm in a functional, for example, in a functional programming framework. So this was just an example of how we define the semantics of the terms in BDL. So we also define the semantics of chaining estimation, which is a closed decomposition of each of the estimations that can be chained together. And at the end, we also define the semantics for the updated steps in a similar manner. And at the end, what we have is the interpreter for the BDL that as a result of having this interpreter, we can get the semantics of the entire backup diagram, which can be considered as the specification for a TD algorithm. So we can have the composition of different types of terms that can give us the description of different algorithms, TD algorithms, and automatically using the BDL interpreter, we can get the specification of those algorithms based on the semantics that we have defined. So we use this for the specifications that we have now for property-based testing. So we write our test in Scala check using a Scala check because our implementation is in a Scala. So I will just explain that what type of properties we test in our framework. So we write first two categories of properties, the properties that are concerned with RL problems and the properties that are concerned with RL algorithms. And then we also separate these categories into generic properties and specific properties. So generic properties are the properties that can be applied for any RL algorithm or RL problem. And the specific properties are the ones that can be applied to any RL, to a specific RL problems or a specific RL algorithm. So this is how we categorize the test that we write. So an example of the test that we write is that, so now using the BDL interpreter, we can get specifications of any TD algorithm based on the description that I gave. So given that we have the specification, now we can test easily the implementation of these algorithms. So we have tests that compares the output of learning from for example, the SARSA implementation, which is an example of an algorithm, a TD algorithm, and the specification that was generated using the BDL interpreter. So we just compare their output, which are distributions or probability distributions, and we compare that these distributions are equivalent with each other using a statistical test. And another example, let's say, of a generic test that for RL problems is a closure property for the transition function, which tells us that starting in any state and action, we always end up in a state that is observable. So this is another example of a property that should hold for any transition relation that we define in our RL for our RL problem. And the implementation is also very close to this logical description that I gave. So as you can see here, the description of the test or the implementation of the test stays very close to the logical description. Another example of the generic problems is that after any number of iterations of learning that we have, the values that we observe, the values of the actions in each state that we observe should be within the floating point range. And a test like this, a generic test like this, can help us to find, for example, problems in the implementation of the reward function, which is a specific function in the reinforcement learning algorithm setup. And another example, which is an example of a problem-specific test, is that, for example, for the car example, we can test that forward-moving car cannot move backward by braking, or a moving car cannot move backward by braking. And this is the logical description that tells us that starting with a positive velocity and taking a transition, we always end up in a position that is greater than the original position. And as you can see, this test requires writing some generators, for example, for the position and velocity of the car. And in our framework, we provide templates for the writing agents, and it enforces writing generators from the beginning, which facilitates writing such property tests or such tests for the agents that are implemented in our framework. So our implementation is in Scala 3, and we have many reusable tests, and you can have templates for writing agents, for example, or writing environments in this template. And also, the framework makes it easier to implement new similar algorithms. So we have implementation of several agents that are either like a smaller scale, or some of them are medium scale that are inspired by industrial cases. And all are available in a GitHub repository that is linked in our paper. And in order to evaluate the tests or the test harness that we have, we also use mutation testing to evaluate how good the tests that we have written are. And the results show that the results of the mutation testing show that in 75% of the cases, the mutation score was above 90%. So it shows that we have a test that can find actually bugs that are injected in the implementation. But another interesting result was that in all cases, the generic test, so only using the generic test, we were able to find 48% of the bugs. And this tells us that having the generic test that can be applied for any reinforcement learning problem or algorithm can find almost half of the bugs that were injected in the implementation. So this tells us that using these tests, the developer can have a head start on testing. So what I presented is a formal specification of key elements of the backup diagrams for TD algorithms and a translation of this into a test harness. And our aim is to extend our framework for other reinforcement learning algorithms, to other classes of reinforcement learning algorithms, and also consider richer value function representations, because currently we are considering tabular representations. So we would like to move towards more deep reinforcement learning algorithms. So yeah, thank you.
We have some time for questions. So I have one question. I was wondering, in other applications of property-based testing, there are systems like for instance, small check that have some notion of exhaustive coverage that checks all test cases up to a small size in a discrete domain, or other things that measure code coverage after running quick check. So I'm wondering, have you thought about is there any way of quantifying coverage for the sort of continuous state spaces you have here? Is there any way of measuring how much of a state space has been explored by a run of this testing?
Yeah, this is a very good question. So far, no, we have not considered, for example, measures of coverage at the moment. But because we are also, for example, in our calculation, we mostly consider observable states, which discretizes the continuous state space into, let's say, a discrete set of states. So it shrinks the state space that we have. But yeah, I mean, we could consider that so far we have not. But yes, this is an interesting idea that we could consider maybe coverage to see how much of the state space is covered while we are testing, or the test that we've written, how much they cover, which part of the state space they cover. Yeah.
Okay, thank you.
Hi there, Marshall. I'm Simon Peyton-Jones at Epic Games. So I've got two questions really. One is that you, I really like the way you tried to formalize what a reinforcement learning algorithm is, because I've read quite a lot of papers about reinforcement learning, and it always frustrates me how informal it is. But my question is, how have you found any take up from the reinforcement learning community? Have they fallen upon this formalism with glad cries, saying, "At last, we can write, algorithms we can understand," or have they just ignored you completely?
Oh, you mean the effect or the impact of our work on the community?
I wasn't so much meaning the testing bit. I was just meaning your language, BDL.
Right.
Formalize it. I mean, well, one might hope that the reinforcement learning community itself, which is, is big these days, would say, "Oh, fantastic! We'd love to use this." I
would be very happy if this happens. I mean, so far, well, of course, this is very new work, and we are covering TD learning algorithms and the tabular representation. Maybe this is a smaller, so given how vast the reinforcement learning field is, and how much, for example, now the deep learning algorithms, how popular they are. So I can imagine that this is just a subclass of algorithms. And I think so far we have not presented the work more in the, let's say, the reinforcement learning community, like the hardcore machine learning community. But I think if we move the work also towards, my hope is that if we move the work towards also formalizing more deep reinforcement learning algorithms, then maybe we can really catch some the attention of the community as well. But I really see, because once we started implementing the algorithm, we really realized there are problems in the presentation of the algorithms, and this is what the feedback that we have got, at least from our community, maybe is the same. So once you start implementing, you would realize that there's a lot of problems in the current presentation.
Yeah. So good for you. Yeah. They need you. They need you a lot. Have we got time for one more? No, but why don't you go?
Good. Thank you. Hey, thank you for a great talk. I was just going to ask a question about the specification of the solutions. And I mean, we do a lot of work in deep neural network specifications, deep neural networks, which are used for often used for reinforcement learning algorithms. And then in the community, there's been various degrees of futility trying to actually formally verify specifications of neural networks. I was wondering whether there was any equivalent work in the tabular-based approaches to reinforcement learning of actually taking a specification, like you can write down in your language, and checking formally whether the neural network, whether the tabular representation actually is guaranteed to obey the specification, and if not, what would be the difficulties of extending your framework?
So I think the specifications can be used both for testing and verification. So we use testing because testing is usually like, given the setup that we have, looked more appropriate, at least for finding bugs for us in the implementation. But it's not so. The specifications are not necessarily for testing. They can be also used for verification. We have not done verification so far, but at least for the tabular representation, the current specifications can be used for verification as well.
Okay, great. Are you aware of any work that
no, so far no,
the tabular representations?
No, so far at least not.
Okay.
I mean, not using a specification like this. That would not like this. At least I can tell you that.
Cheers. Thank you very much.
Okay. So it's me again. I got another question about what success looks like. So I guess in a reinforcement learning algorithm, you described, just bugs in the implementation as being something you'd like to discover. But quite often a bug in the implementation might simply mean it doesn't learn as well as it could. I mean, there isn't a crisp criteria for it succeeds or it doesn't succeed. It's just, the car doesn't brake as smoothly as it does, or the little figure doesn't find its way through the maze as effectively. So it seems hard to test whether there are bugs in the implementation of a reinforcement algorithm, unless they're sort of catastrophic bugs. That mean it, simply falls over dead and has seg faults or something. How can you get at any of those kind of just the more insidious bugs?
I mean, I totally agree that it is difficult to test this type of algorithms. And so far, I mean, we have come up with some properties that are like, for example, the example of the generic properties that we showed for testing a specific components in the reinforcement learning algorithm. But looking at the whole process as a whole, for example, if you look at the obtain policy and you see that something is wrong, it is true that it is difficult to detect maybe that something is wrong in the policy. But there's a body of work that actually works on the evaluation of the policies. But I think our work would be on the side of those works. So it's just mainly assuming that something is like the existing work discovered that there's something wrong with the policies that have been obtained, then our work can be on the side to find at least some of the bugs based on the properties that we have defined so far that we know should be satisfied for any type of, let's say, the var function or any type of implementation of the transition function. Then that can help. I would say it would be just like a work on the side that can help with discovering at least a part of the bugs that can cause that can find the cause for the policy being the wrong policy, I would say.
Thank you.
Thank the speaker again.